Hello, welcome to the 7th class of this course. So in this class, I will solve another example regarding in the context of Frobenius method. So if we are given a second order differential equation and we are asked to find out a power series solution at a regular singular point, then we will apply this Frobenius method. Okay, so let's take a differential equation, where we have to apply this Frobenius method. So okay, so I will write it as example 2. Okay, so the given differential equation is 2x, and I will ask you to solve it along with me. In that case, it will not be boring. Plus 2y equals to 0. Okay, y double dash means d2y dx2, and y dash is dy dx, where y is basically a function of x. Okay, and we are asked to find out, so find series solution at x equals to 0. Good. So this is our px. Okay, px is equals to 2x. This is our qx, which is 1 minus 1. So qx is minus 1, and this is our rx, which is basically 2. So this is basically a constant function of x. Qx and rx are constant functions of x. So it doesn't depend on x, but we can still write it as a function of x. Okay. Good. So let's check whether, so we are asked to find out a power series solution at x equals to 0, right? So let's check whether x equals to 0 is an ordinary point or is a regular singular point. Okay. If it's an ordinary point, then we will follow the usual method, like we will assume the solution as sum over a n x to the power n tends to n equals to 0 to infinity. And if x equals to 0 is a regular singular point, in that case we will assume that, okay, it will be n plus s, okay, where this s is a constant that we need to determine. And if x equals to 0 is an essential singular point, in that case we will not find any power series solution. Okay. So let's calculate qx by px equals to minus 1 divided by 2x, and as x is, and at x equals to 0, it tends to, it diverges basically, so the limit doesn't exist at x equals to 0. Okay, so that means it is not analytic. Qx by px is not a analytic function at x equals to 0. Similarly, rx divided by px equals to 2 by 2x, that is 1 by x, right? And again, it is not analytic at x equals to 0. At x equals to 0, the limit will diverge. Analytic means the limit exists, finite limit exists. So these two ratios or these two functions are not analytic at x equals to 0, right? So that means x equals to 0 is not an ordinary point for this differential equation. Okay, so let's check whether it's a regular singular point or not. So in that case, what we need to do is we need to calculate times x minus x naught. Okay, but x naught is 0 here. We are asked to find out a power series solution at x equals to 0. So the x naught is 0. So that means it is just x, so which is minus half, and it is, it's an analytic function. It's always half minus half. So it's an analytic at x equals to 0. And similarly, rx divided by px times x minus x naught whole square, and x naught is 0 again, so it is x square equals to just x, and x is an analytic function at x equals to 0. So both are analytic. So both are analytic. Both are analytic at x equals to 0, which implies that x equals to 0 is a regular singular point for the given differential equation. Okay, so as it is a regular singular point, we will apply Frobenius method. We will apply the Frobenius method. And what is that? We will start with a series which is sum over n equals to 0 to infinity a n x to the power x minus x naught to the power n plus s, and x naught is 0, so in that case it will be x to the power n plus s. Okay, so this s, so we need to determine these two things, like s, this s we need to determine, and this a n we need to determine. Okay, from this differential equation. So this is how we will start, and now we need to put it in the differential equation. For that, we need to calculate this y dash and x y double dash. Okay, so that's what we will do now. So if we calculate y dash x, okay, equals to n equals to 0 to infinity n plus s a n x to the power n plus s, right? So n plus s minus 1. So okay, the summation which will start from n equals to 0. Okay, because for n equals to 0, from n equals to 0 to infinity, this this term will not be 0. Basically, we cannot say anything about it, whether it will be 0 or not. Okay, because of this s present here. And you can also observe that, okay, here it has a power of x has a power of n plus s minus 1, right? And the second term that we are writing, which is just y dash. So what we need to do is we need to write it in such a way that x has a power of n plus s. That's what we want, because we want to compare, right? So in that case, what's the method? So n is the summation index, so we can write, which is basically a dummy index. So I can write n minus 1 equals to, s is a constant. Okay, so I can write it as m, right? That means n equals to m plus 1. Good. When if n equals to 0, m equals to minus 1, and if n tends to infinity, m also tends to infinity. Okay, So now replace this summation. So from m equals to minus 1 to infinity, I am replacing n by m. So n equals to 0 means m equals to minus 1, right? So that's what I am doing right now. And n plus s, so n is m plus 1, so I am writing it as m plus s plus 1 a m plus 1 x to the power m plus s, right? And now m is a summation index. I can just write it as n equals to minus 1 to infinity n plus s plus 1, sorry, a n plus 1 x to the power n plus s. This is our y dash x. Good. Now what we will do is we will calculate y double dash x. So y double dash x will be n equals to minus 1 to infinity n plus s plus 1 times n plus s a n plus 1 x to the power n plus s minus 1, right? Just read ddx of y dash x. Good. Now the first term is basically 2x y double dash, right? So 2x y double dash is sum over n equals to minus 1 to infinity 2 n plus s times n plus s plus 1 a n plus 1, right? Yeah, a n plus 1 x to the power n plus s. Okay, so now you can see this is the first term, it has a power of x to the power n plus s. This is the second term of the differential equation, that is y dash x, okay, with a minus sign. So it also has a power of x to the power n, so x here also x has a power of n plus s. And the third term is 2i's y and y, so this is a y, so it also has a power of x to x, here also x has a power of n plus s. Okay. So we don't need to do further index shifts, we can just write them together in the differential equation. Okay, so if I just write them together in the differential equation, the differential equation is 2x y double dash minus y dash plus what's that, 2y equals to 0. Okay, and now I am putting these values, that is n equals to minus 1 to infinity 2i's n plus s minus plus 1 a n plus 1 x to the power n plus s minus y dash is this term, so which is sum over n equals to minus 1 to infinity n plus s plus 1 n plus s plus 1, okay, times a n plus 1 x to the power n plus s, okay, plus this 2y term, and y is, so it is 2 times sum over n equals to 0 to infinity a n x to the power n plus s equals to 0. Okay, so you can see that we cannot put all these summations together, because here it is starting from n equals to minus 1, here also it is starting from n equals to minus 1, so we can put these two terms together, but this term it is starting from n equals to 0. Okay, so though x has a power of n plus s in all these terms, the summation index, it is not starting all from n equals to 0. Okay, so we need to take care of that, but before that let me put these two terms together. Okay, so these two terms, let me put them together. Okay, these two terms, these first two terms, so if I put them together, then it will be sum over n equals to -1 to infinity. Okay, I can take this n plus s minus 1 common, so it will be n plus s plus 1 common, sorry. I can also take n plus 1 common, x to the power n plus s common. So in that case, we are left with twice n plus s plus 2s, twice n plus 2s minus 1, okay, and plus this term, so which is 2 summation n equals to 0 to infinity a n x to the power n plus s equals to 0, right? So this is what we have. Yeah. So now what we will do, this term is starting from n equals to -1. So what I will do is I will write minus 1th term separately. So I will just put n equals to -1. So in that case it will be just s, and it will be if I put n equals to -1, so it will be twice s minus 3, right? So it will be s times twice s minus 3 times a 0, because I am putting n equals to -1, it is a 0, and it is x to the power s, sorry, x to the power s minus 1, right? And then I can write the other terms like n equals to 0 to infinity. So all other terms will be in this summation. It will be n plus s plus 1 twice n plus twice s minus 1 a n plus 1 x to the power n plus s, okay, plus this term, this twice n equals to 0 to infinity a n x to the power n plus s equals to 0, okay. So basically what I did is I wrote these terms which was starting from n equals to -1 to infinity in this form. So now it has a n equals to -1th term here, and then all the other terms are written here, okay, and the last this term is here, okay. Good. So now what we will do is I will just write s 2s minus 3 a0 x to the power s minus 1 plus, now you can see these two terms, this term and this term, now we can put them together, because here x has a power of n plus s, here also x has a power of n plus s, and both are starting from n equals to 0, okay. So now let's put them together, and I put them together, it will be sum over n equals to 0 to infinity n plus s plus 1 twice n plus twice s minus 1 a n plus 1 a n plus 1 plus twice a n, okay, times x to the power n plus s equals to 0. Right. Good. And now what we will do is we will make these coefficients 0, okay, because the right hand side is 0. So the coefficient of x to the power s minus 1 is also 0, which is like this term is 0, and these terms are also 0, okay. So for this one, the coefficient of x to the power s minus 1, if I make it 0, so it will be s into twice s minus 3 equals to 0, right, because a naught not is equal to 0, I am assuming a naught not is equal to 0, okay. So in that case s will be 0 comma 3 by 2. Two solutions, two values of S are possible. So S will be 0 or 3 by 2. Now if I take the coefficients of x to the power n plus s 0, sorry, that is this term 0, we will get the recursion relation. Okay, we will get the recurrence relation, that is n plus s plus 1 twice n plus twice s minus 1 an plus 1 plus twice an equals to 0, implies an equals to, sorry, an plus 1 equals to minus 2 divided by n plus s plus 1 times 2n plus 2s minus 1 times an. Okay, so this is our recurrence relation. So this is our recurrence relation. So what this recurrence relation says is basically, it's a very simple recurrence relation. Like if we have a0, a1, a2, a3, a4, a5 dot dot dot. Okay, so a0 not is equals to 0, right? So I will start from a0 then, and if I start from a0, this recurrence relation says is basically from a0 it can go to a1. From if we are given an, then we can find out an plus 1. That means I can go from a0 to a1. If a1 is known, then I can go to a2 from there. If a2 is known, I can go to a3. If a3 is known, I can go for a4, and like that. Okay, good. So now we have, so S can take two values, one is s equals to 0, another is s equals to 3 by 2. Okay, so let's see what happens if s equals to 0. Okay, so the recurrence relation will be then an plus 1 equals to minus 2 divided by n plus 1 times 2n minus 1 an. This is now our recurrence relation. I have put s equals to 0 here. Okay, right. So now what we will do is, we will start from a0 because a0 not is equals to 0. So we'll start from a0, and then this recurrence relation will tell me what is the value of a1, right? So if I can find a1 equals to minus, so to get the value of a1 I need to put n equals to 0 in this recurrence relation, right? So I am putting n equals to 0 in this recurrence relation. This is the recurrence relation for s equals to 0, right? So I am starting from a0 and I am putting n equals to 0 in this recurrence relation. So it will be a1 equals to minus 2 divided by, so it is 1 times minus 1 times a0, right? N equals to 0 I put, so it is basically twice a0. Okay, this is a1. If I put n equals to 1, so then the recurrence relation says that okay, it will give me a2, which equals to 2 divided by, so n equals to 1, that means it is 2 times, so twice n is again 2 minus 1, that is 1 times a1. So it is giving me a2 in terms of a1. Okay, and I know a1 is twice a0, so I will put the value, so 2 cancels, and if I put 2 a0, it will be, instead of a1, so it will be minus 2 a0. Okay, and if I put n equals to 2, then from the recurrence relation you can see I will get a3 equals to minus 2 by okay, let me follow a pattern here. Okay, so you can see I am writing this 2 here as it is, so it will be then 2 square, it will be then minus, so if I put a1 as twice a0, so then it will be 2 square divided by, so 2 times 1 is basically 2 factorial a0, right, which is same as minus 2 a0, but I am writing this because it will follow a pattern. Okay, so because in the denominator it has n plus 1 times 2n minus 1. Okay, so it will follow a pattern, and this will also follow a pattern. So it is then a3 is 2 times, okay, n plus 1 is 4 times 2n minus 1, and 2n minus 1 is, so 2n is 6, sorry, n is 2 here, so n plus 1 is 3, and 2n is 4 minus 1, it is again 3, right, so which equals to times a2, now a2 I know is this, so it will be, it equals to then 2 cube divided by 3 times 2 factorial, that is 3 factorial a0. Okay, if I put n equals to 3, then a4 equals to, so an plus 1, that is a4, okay, n equals to 3, minus 2 divided by n equals to 3. Okay, so n plus 1 is 4 dot n equals to 3, so 2n is 6 minus 1, that is 5. Okay, so it equals to minus 2 to the times a3. Okay, n is here, so times a3, and a3 is this, so it will be 2 to the power 4, so a3 has 2 cube here, so it will be 2 cube times 2 times this 2, that is 2 to the power 4, and then 3 factorial times this 4, so times this 4, it is 4 factorial. Okay, so this 3 factorial times this 4, that is 4 factorial, and there is this 3 times 5. Okay, 3 times 5, so this is basically our times a0, so I'm writing this a3, putting this a3 here. Okay, so it is following this kind of pattern. Okay, so I can write it as, 1 times 2 factorial, something like that. Okay, just write it as 2 factorial, no problem. It will follow this kind of pattern. So it basically gives you the y for s equals to 0, the solution will be a0 x to the power s. Okay, let me write it in the summation form first. So summation n equals to 0 to infinity an x to the power n plus s. Okay, and which means a0 x to the power s plus a1 x to the power n 1 plus s, or rather s plus 1 plus a2 x to the power s plus 2 plus a3 x to the power s plus 3 plus a4 x to the power s plus 4. Okay, and s is 0, so it means it is basically a0 plus a1 is 2i's a0, so plus 2i's a0 x, because s is 0, right? a2 is minus 2 square divided by 2 factorial, so minus 2 square divided by 2 factorial times a0, right? Yeah, x to the power x square, s is 0, plus a3 is 2 cube divided by 3 times 3 factorial, so 2 cube divided by 3 times 3 factorial times x cube minus 2 to the power 4 divided by 3 times 5 times 4 factorial x to the power 4, right, plus dot 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 all the other terms. And so it means I can write this a0 outside, I can take this a0 common, and the series will be, so y at is for s equals to 0, it will be 1 plus 2x minus 2 square divided by 2 factorial times x square plus 2 cube divided by 3 dot 3 factorial times x cube minus 2 to the power 4 divided by 3 times 5 times 4 factorial x to the power 4 plus dot dot dot. Okay, this is one solution for s equals to 0. So s can take two values of, if you remember, 0 and 3 by 2. So let's see what happens if s equals to 3 by 2. S equals to 3 by 2. Let's write down the recurrence relation. So okay, we will always start with a0. Okay, a0 not equals to 0. So this is the condition, a0 not equals to 0. Good. So the recurrence relation is an plus 1 equals to minus 2, let me check it again, 2 divided by n plus s plus 1, 2 divided by n plus s plus 1, and there is an sitting here, and sorry, an sitting here, and 2n plus 2s minus 1. Okay, so 2n plus 2s minus 1, 2n plus 2s minus 1, 2n plus 2s minus 1. Okay, now if I put s equals to 3 by 2, then the recurrence relation will be 2 divided by n plus 3 by 2 plus 1 times 3, so 2n plus 2 times 3 by 2, s equals to 3 by 2, right? So 2 times 3 by 2 is 3 minus 1 an. Okay, now 3 by 2 plus 1, which is 5 by 2, right? And n plus 5 by 2, which is, I can write it as n plus 5, twice n plus 5 divided by 2. So this is how what I will write here. So 2n plus 5 divided by 2 times 2n plus 2. So this 3 minus 1 is 2. Okay, so I am writing is 2n plus 2 times an. Okay, I'm writing all these things. Okay, so now I can take this 2 common from this term. So if I take this 2 common, then it will be n plus 1 times 2, and this 2 cancels. So the recurrence relation is an plus 1 equals to minus 2 by n plus 1. I'm writing this term first, and then 2n plus 5 times an. So now this is the recurrence relation for a is equals to 3 by 2. Okay, and we will start from a0, right? So if we start from a0, okay, let's start from a0 then. So in that case, a1 will be, so to get a1, I have to put n equals to 0. So you can see this recurrence relation is valid for this equation, the summation. It is from n equals to 0 to infinity, and this recurrence relation, it comes from there. Okay, so in that case, this recurrence relation, it is valid for n greater than equals to 0, and that's what here we did. We started putting n from 0. Okay, here also that's what we will do. So this recurrence relation, it is valid for n greater than equals to 0. So we'll start putting n equals, so we'll start putting n from 0. Okay, so if I put n equals to 0, it will be a1 equals to minus 2. So if I put n equals to 0, it is 1 and it is 5. Okay, so it will be, so it is 1 times 5 times a0, right? Then if I put n equals to 2, sorry, n equals to 1, so then a2 will be minus 2 divided by, so 1 plus 1 is 2, so it is 2 dot, and 2 times 1, that is 4, sorry, 2 plus 5 is 7 a1. Okay, and so if I put the value of a1 here, it will be plus 2 square times 1 dot 2 dot 5 dot 7. Okay, 1 times 2 times 5 times 7 times a0, right? So I'm writing it in this way because it will follow a pattern. That's the motivation. If I take n equals to 2, in that case a3 will be equals to 2 times 2 divided by, so if I put n equals to 2, it will be 3, n plus 1 is 3, so that is a3 equals to 2 divided by 2 plus 1, so 3, this is 3, so 3 times 2 times 2 is 4 plus 5, that is 9. Okay, so it is 9, 3 times 9 a2. Okay, and now a2 we know this, so it will be minus 2 cube divided by 1 dot 2 dot 3, so 1 times 2 times 3 times 5 times 7 times 9. So now you can see it is following a pattern. So for a3 it is, so it will be 2 cube, 2 to the power 3 divided by 1 times 2 times 3, and then it is 5 times 7 times 9 times a0. Similarly, if I put n equals to 3, so then it will give me a4 equals to minus 2 divided by, okay, so n equals to 3, so it means 3 times 3 plus 1 is 4, so it is 4 times, and 3 times 2 is 6, 6 plus 5 is 11 a3 equals to, and then I will put the value of a3, which is plus 2 to the power 4, because there is 2 cube here. Okay, so 2 to the power 4, 1 times 2 times 3 times 4 times 5 times 7 times 9 times 11 times a0. Okay, so in this way it will proceed. Basically, you can now see the pattern, follow the pattern. Okay. So then basically the power series solution for s equals to 3 by 2 is basically sum over an x to the power n plus s, where s equals to 3 by 2 and n equals to 0 to infinity. So I can write this x to the power s outside, so it will be an x to the power n equals to 0 to infinity, okay, which is basically x to the power 3 by 2 times a0 plus a1x plus a2x square plus a3x cube plus a4x to the power 4 plus dot dot dot, okay. And I can write this a0 outside because in all these terms a1, a2, a3, a4, a0 is common, right? So it is a0 times 3 by 2 and then 1 and a1. What is a1? A1 is this term. So a0 I have already put outside, so it will be minus 2 divided by 1 times 5, 1 times 5 times x plus a2 is 2 square divided by 1 times 2 times 5 times 7, okay, just following the pattern. And a0 I put already outside, so then it will be x square, okay, minus a3 x cube. So what is a3? a3 is this, so 2 cube, so there is a minus sign, then 2 cube divided by 1 times 2 times 3, okay, so 1 times 2 times 3 times 5 times 7 times 9, okay, 5 times 7 times 9, and a0 I already put outside, so it will be x cube, okay, then plus a4 is this term, okay, so it is 2 to the power 4, just follow the pattern, 1 times 2 times 3 times 4 times 5 times 7 times 9 times the next odd term, that is 11, x to the power 4 minus dot 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 all other terms. So this is our second independent solution for s equals to 3 by 2, and the general solution will be then will be then y equals to alpha y for s equals to 0 plus beta y for s equals to 3 by 2. This is the general solution, and you can just write the series, already it is written here, you can just write for, if you want to do it, formalize it, okay. So this is how we can get, so here these two are power series at x equals to 0, okay. So this is how we can get a power series solution using the Frobenius method if we are given a differential equation and asked to find out a power series solution at a regular singular point, okay. And here also you can see, because it's a second order differential equation, we are getting two linearly independent solutions and all linear combinations of those, that is alpha times one solution plus beta times the other solution. So depending on the values of alpha and beta, I can generate all other solutions. So it's like two independent vectors in 2 dimension I'm given, and I can expand the whole 2D space using the linear combination of these two independent vectors. So these two solutions are acting like two independent vectors, okay. So you can think like that, okay. So this is how we can solve. Basically, we can, if we are given a differential equation, second order differential equation mainly, and we are asked to find out a power series solution at around some point or at some point. This is how we need to do. Okay, so first we need to check whether the point where we are asked to find out the power series solution, so whether the point is an ordinary point. If it's an ordinary point, then we will assume, okay, the solution then will be sum over a n x to the power x minus x naught to the power n. Okay, n equals to 0 to infinity. We'll start with that. If that's not the case, if the given point is a regular singular point, in that case we will start with n plus s and we'll use the Frobenius method. Okay, and if it's a irregular singular point or an essential singular point, then we cannot find a power series solution at that point. Okay, so that's all for how to find out a power series solution. So next what we will do is we will take some special equations. For example, from the next class I will start with the Legendre differential equation, and I will solve it. I will get the power series solution, which I will call Legendre functions. Okay, and we will study different properties of that Legendre function. So that's our next topic. Let me give some homeworks so you can try it yourself. I'm just writing them from exercise from Boas. Okay, the first one is x square y double dash plus x y dash minus 9y equals to 0. Number 2 is x square y double dash plus 2x square y minus 2y equals to 0. Y dash is dy dx and y double dash is d2y dx2. Okay, this is y dash. And number 3 is x y double dash minus y dash plus 9x to the power 5y equals to 0. And number 4 is x square y double dash minus x square plus 2 times times y equals to 0. Okay, so for all of these differential equation, so we are asked to find out power series solution. Power series solution at x equals to 0 if it exists at all. So first of all, you need to check for ordinary point. You need to check for if it's not an ordinary point, you need to check for regular singular point, and then you need to apply the corresponding methods, and if it is none of them, if it's an essential singular point, then you cannot find power series solution. Okay, so that's all for today.